So I'm going to ask you how you did these problems in a second, but one of the things that I want you to keep in mind when working with rational expressions is that they're just fractions underneath, right? Yes, they have variables, they have algebraic expressions on the top and the bottom, but they're fractions. And so if you are solid in your understanding of how to work with fractions, which if you're not, you will be, especially after this unit is over, those processes that you use to manipulate fractions all import to this directly, right? If you know how to add two fractions, then you know how to add two rational expressions. If you know how to multiply fractions, you know how to multiply rational expressions. If you know how to simplify a fraction, you know how to simplify a rational expression. It looks more complicated because there are variables, but the processes, the step-by-steps underneath them are all the same. So as we work these examples, I also want to, in parallel, work examples of doing those same tasks just with numerical fractions instead. So let's start with the simplify step in question 1. How would you approach the process of simplifying that rational expression? Robert.
Factor out the GCF.
All right, factor out the GCF of what? Where are you looking here?
Both the top and the bottom, but you can start wherever, really.
Okay, start wherever. Factor the GCF out of everything. In fact, I'm going to take that a step further and just looking more broadly. Factor everything in sight. The first thing you do when you see a rational expression, if it's not already factored, factor it. Because we can make very little progress in dealing with fractions or rational expressions unless we know where all the factors are in the numerator and denominator. And factoring as a general strategy starts by identifying and taking out the GCF. So what GCF can we take out and where can we take it out? Here.
I'd say for the top, we'd be able to take out 4.
Okay. So the top has a GCF of 4, and if I factor out 4 from 4x squared minus 36, what's left over? X squared in the first term. Yeah, x squared minus 9. There we go. So now I've taken the GCF out of the numerator and it turned into 4 times x squared minus 9. How about the denominator? Is there a GCF to take out there? X squared plus 2x minus 15? Yeah, there's no GCF that we can take out of those 3 terms, right? So at that stage of the factoring process, this denominator doesn't change. And now that we've done the GCF factoring, how do we take this still further? How can we factor this more? Let's start with the x squared plus 2x minus 15. Start with the denominator. How can we split apart x squared plus 2x minus 15 to discover its factors? What's the trick?
Sum and product.
Sum and product?
Oh no, you were on top.
I'm looking at the bottom one right now, just for the sake of getting started. Let's play the sum and product game, yeah.
-5. No, +5 and -2.
Positive 5, negative 3, because those multiply together to give you negative 15, and they add together to give you 2, which is why they're the right combination of numbers, right, to factor that denominator. And once I have those numbers,
So you have to find the greatest common factor and also a number, the 2 numbers that...
yeah, it's a 2-step process. Well, I mean, it could be a multi-step process to factor something completely, but the GCF is always a good choice to do first, right? Once you take the GCF out, if there is one, then start looking for other ways to factor what's left. So now my denominator has been factored into x plus 5, x minus 3. How about the numerator? What about this x squared minus 9? How does that factor, Robert?
You could break that x squared minus 9 down a little further, so you could do 4 parentheses x plus 3, and then x minus 3.
Yeah. That's technically was something we saw in Module 8 as the difference of squares special factoring technique, right? Because x squared and 9 are both perfect squares. We can break them apart using the perfect squares, difference of perfect squares formula. The other way that I sometimes like to frame that is just by seeing it as we need to factor x squared, which you can do as x and x. We need to factor negative 9, and there are several ways to do that, but if we try splitting it apart into negative 3 and 3, then the cross terms, if we were to FOIL that out, would be 3x and minus 3x, which would cancel one another out. And therefore, when I multiply x plus 3 by x minus 3, I'm going to get x squared minus 9. So now we've factored the numerator completely. We've factored the denominator completely. In the analog, when we're working with rational numbers, we might say, well, what is 75? Well, 75, we can factor out a 15 times 5. And 120 we can factor out as 15 times 8. I think that's right. Yep. So this is the stage that we would be at right now if we were simplifying the fraction 75 over 120. We find out what are some of the factors and we factor them out. What happens next? We haven't actually simplified anything yet. How do we simplify this now?
You can reduce
Reduce. What does that mean? What does that look like?
the 15 to 50.
Yeah, if we're looking at this fraction on the right, reducing means canceling out any common factors that exist in the numerator and the denominator. 15 times 5 and 15 times 8 have a common factor of 15. So, if we divide both the numerator and the denominator by 15, it reduces the fraction by canceling out that common factor. So how do we bring that home to our more complicated problem? What common factor or common factors can we cancel in this rational expression?
Negative. No, x is negative.
Yeah, and so here's a key observation, is that once we've factored everything, that divides our expressions on top and bottom into sets of factors, and each factor has to be canceled either completely or not at all. So it's not as though I can take just the x or just the 5 and try to cancel those things. These factors are now indivisible on their own. If I'm going to cancel x minus 3, I have to cancel all of x minus 3. And in fact, as Dat was saying, x minus 3 is the common factor that exists in the numerator and denominator in this example. And so we can and should cancel out the x minus 3's to make this fraction simpler. And so the answer, right, we would just peel the x minus 3's away. And I personally would be okay with leaving the answer in this form. 4 times x plus 3 over x plus 5. I suppose if you wanted to simplify it one step further, you could, redistribute this 4x plus 12 on top, and x plus 5 on the bottom. But again, the parallel that I want you to keep in mind is that this process really is little different from what you do when reducing fractions. Right? Discover the factors, break apart the numerator and the denominator into their multiplicative pieces, and then any multiplicative pieces that are shared by both the numerator and the denominator can be crossed out to reduce the fraction, which was simple to do, and we could see that 75 and 120 were both divisible by 15, which we can reduce to 5 over 8. And once we've factored the numerator and denominator, that's the hard step in working with rational expressions. The factoring is what's going to screw you up the most. It's where you're going to spend the most of your thought. But once you've achieved that, then just canceling out the common factors makes your rational expression simpler.